Usually we always ask the people the same type of questions, because then on the EATCS website, people can look at the answers of different people for this kind of question.
No, nobody's going to compare. You think people are going to look at my answer and Kurt Meller's answer and compare and analyze? Maybe historians, but
you're right. Maybe you're right. Yeah.
One reason that I like to do it like conversationally is because it gives you more flexibility. I mean,
That's true.
you ask a questions and I answer, and that inspire a question that you not think in advance.
That makes sense. That makes sense. No, I totally prefer this actually too.
That's one reason I teach without slides. I teach on the board.
Ah, okay. Really?
What's called as we call old school. Okay.
Nice.
And one reason is I have flexibility. If student ask a questions, I can go and expand on it.
Right.
Sometimes I get a new idea while I'm talking, and suddenly a new idea come to my head and I go on a tangent. So I have infinite flexibility. So
that makes sense. Which classes you use them in all of the classes, this approach, or?
I usually like to do, even I do, if I did summer school, I used to teach on the board. It just the other reason I like to teach when you have to write it, it automatically slows you down.
Right, that's actually a good point indeed.
You can't rush ahead because you have to write everything down yourself.
Right.
So it's a very fantastic control mechanism for the speed of the teacher.
Right, that's true. Do you do it on a projector or you write it on the blackboard?
No, projector is cumbersome. I write on the board. We have whiteboard. I write it on a whiteboard. I could use a chalk, but now people don't put chalkboards anymore. They put whiteboards. So.
Did you practice that, or because I usually go like not very horizontal if I do that.
No, I'm pretty good at it, and you have to know the material well. So you don't. I mean, I don't want to sit with my notes and copy my notes, because then people says,
right,
just give us the notes. Why do we need you?
That's right.
So it's everything. It's
okay. Nice.
I call it improvisational theater. Everything is an improvisation. So
right. And if the students know this, they also pay more attention, because maybe they try to spot a mistake or something like that, right?
Yeah. So the
it's
students
also more interactive.
And I give them later the lecture notes, so they can later. I tell them you don't have to take detailed notes.
Yeah.
I've lecture note, everything is written, but this way it's more dynamic.
Yeah.
Dynamic teaching. It's more interesting if you just.
No, I agree. I think that's. And you did it always like that, or you changed your approach over the years?
I never used slides in teaching. I use slides, of course. When you give talks, it's very different. You have an hour. You have to pace yourself.
Right.
So there, I use now PowerPoint or LaTeX. But teaching, I'm trying to remember. No, I always taught on a board. When I was an undergraduate student, first year, I was a physics major, and my professor used transparency. Do you know what transparencies are?
No, I don't think so.
So these are
yes, of course,
plastic sheets.
Yes, of course,
you put an overhead projector.
Right. One after the other. It's always one page, right?
Right. And this was then the new technology. And he liked it because you prepare it once and then you can reuse it. Okay.
Right.
But he was going way too fast. Because after you write the slide, you look at them. Oh yeah, everything is obvious here. So you go very fast, and I just have trauma from these days where it was going so fast. You couldn't follow. So I said I'll never do that. So I always taught using the board.
Right.
Yeah.
Could you in transparency? You could also fill out things in principle, right? But you could have like a template and fill it out.
Yeah. There are people who do it, and I mean there are some advantages. Also, people that say they like to use PowerPoint because they have some like animation and things like that. But I just what I do is very symbolic, not graphical. So I really don't need so.
But it's quite rare that people have this approach, right? Or you think it's becoming more popular at Rice?
I think one of my students wrote to me that she taught her first course and she said she'd use that approach and she's very happy with it. Yeah.
Nice. Great. Actually, one of the questions we always ask that you almost answered already, is there something that probably most readers of the bulletin don't know about you? That
I mean, there are some personal things that people may not know about me. I'm a second generation Holocaust survivor. And you can find on YouTube a talk that I give describing how my parents survived the Holocaust. I served 5 years in the military. So some people think that sometimes some people think I'm too assertive. Some people think of me as a bit too assertive. Then I'm a military officer. So let's explain my assertiveness. I think these are two personal details. I mean, they're not secrets, but I don't know that necessarily they're well known.
And 5 years, that is unusually long, of course, even for Israel. But that's like when you become an officer, it's always 5 years then, right? Or it used to be at that time?
Not necessarily. So one is if you want to become they're normally 3 years for men. If you want to become an officer, then you have to sign up for some more. But then after your regular service, you also have to do what we call reserve duty of about 1 month per year. So the 5 years is cumulative. I sat down once and I tallied up, okay, how much time did I spend in the military?
Yeah.
And it's about 5 years.
And up to which year you have to do this on a yearly basis, this 1 month up to?
Most men do it roughly until the mid-40s. But I came to United States, so that was kind of the end, pretty much the end of that, yeah.
Yeah, and you did this officer career before Bar-Ilan, or then during your studies?
He was part of it. So I was involved. There is something called in the United States, we call it, in Israel, it's called academic reserve. And the idea is to basically, most people finish their service and then they go to school.
Right.
And academic reserve says that you actually switch it. You first go to school, and then you do the service.
Yeah.
So you postpone your service, and from the military point of view, they get better educated officers.
Okay, that makes sense actually.
And then during the service, you do reserve duty in the summers.
Yeah, okay.
Okay, so you do part of the training during the summers.
Yeah. So you don't lose anything in the
right. And then so they get you, ultimately they get more from you than they get otherwise, and they get better educated officers. So in particular,
in which unit were you, or is this confidential?
No, it's not a secret. I was an artillery officer. Yeah. And they usually, that was a traditional trajectory for academic reserve, because artillery is a very technical field.
Right.
And so they like people especially with quantitative background. So physics was ideal background to be an artillery.
Right, of course. That.
Yeah.
So basically you give a choice of preferences and then they select based on your profile there.
Yeah.
Okay, thanks. So that's nice. So typically we also wonder like whether you could mention a paper that influenced you particularly, or something that you recommend other community members to read.
Well, I think one of my all-time favorite paper is a paper with the shortest possible title, Alternation, by Chandra Kozen and Stockmeyer. Late 70s, I forgot the precise year, where they introduce the concept of we have non-determinism, we have condeterminism. They included alternation, when you basically alternated it between the two modes. And it's a very, very beautiful paper. And ultimately, I first read it as a paper in complexity theory, because it's just a very elegant paper in complexity theory. But later on, it turned out that alternating automata, which are also introduced in that paper,
right,
end up
okay.
being a very, very kind of important tool in my work on program verification. So
Yeah.
it started really as a complexity theory, and it's a very elegant paper, and just who can get to write a paper with one word title?
Right.
There is elegance there with finding a perfect one word
Yeah.
title. And then it ended up with the concept of alternation, which is really another way of game playing. Alternation is essentially game playing.
Okay, right. Mm-hmm.
So you take turns between two players, and that ended up being a major theme of my research.
Right.
So
Okay, right. I was not aware that this is actually the root of many of these. So that's also, for example, for games like Stackelberg games or
it's a lot of game. I mean,
syntheses or.
Game came up later also in synthesis. So in synthesis,
Mm,
the game come up as a more kind of, well, there are the two-player game, of course, preceded this concept. I mean, they go back all the way to
Neumann for Neumann or.
Neumann, Morgenstern, and in set theory, they
Mm,
play a role games. But what was new in that paper is to take the concept of a game and make it into a computational construct. Okay. And then to define complexity class, so to get that p-space alternating polynomial time. So this essentially a polynomial time game is give you the power of p-space. So this idea of taking the concept of game and putting it inside the computational mechanism, and that give rise to the using alternating automata as a tool, and it turned out to be a very, very powerful tool, because alternation is very close to logic. Logic has conjunction and disjunction, so the alternation shows up very naturally there. So it turns out that the initial translation, for example, from LTL to Bushy automata was somewhat cumbersome. But today, the way you teach it, you first go to alternating automata, which is very easy translation, and then you show a generic translation alternating automata to
yeah.
non-deterministic automata. So
Mm.
you proceed in these steps, and that's the way to teach it, and even implement it, sometimes implement it that way. But the idea of embedding the game inside the computational mechanism, that was really an idea that came to me from this Chandra Kozen and Stockmeyer paper.
Okay, very nice. I think a lot of people probably in the community don't know this, are not aware of this. Is there a paper of your own that you like to recommend, or that you have a nice story behind that you could share with us?
I mean, my second most cited paper is a paper on complexity of relational queries. And there was a paper that I actually read I published it after my PhD. But it appeared just immediately, like I finished in the fall of 1981, and it appeared in the spring of 1982. But I did the work while I was a PhD student, but it was not part of my PhD dissertation. It was something kind of I did on the side. And it started with this observation that there were different complexity results for relational queries, and they seem kind of contradictory. One result says that first order logic is the complexity of first order queries is p-space complete. And another result said the complexity of existential second order queries is NP.
Yeah.
So wait a minute, p-space is more than NP. This NP is contained in p-space, but second order logic is more expressed in first order logic. So what's going on there? And out of this befuddlement, just not understanding what's going on, came the distinction that there are different ways to measure complexity of queries, complexity in the query, complexity in the data, call it expression complexity and data complexity. And that turned out to be a very fundamental distinction. And really, I did not even realize at the time that was the first paper in what today people call multivariate complexity theory, which is more general term than parameterized complexity.
Yeah. Okay.
But even parameterized complexity today, the preferred term is multivariate complexity, is what happens when your input has different input variables and they have different impact on the complexity. And really the first realization of that is when you do, and in fact today I even call it logical algorithmics, which is the way to think of instead of typically we think of an algorithm. I give you a problem, I describe to you the problem in English, and I'll tell you, perfect matching. I tell you what it is, and you go think how do you find an algorithms to do that. But really there's another way to develop algorithm, which is you just write a description of the property that you want to study. And then there is a generic algorithm, a meta algorithm that takes your query and evaluates it on a structure. This is really what database queries are.
Okay. Yeah.
But you can think about it as a more
mm-hmm.
general way. So
Mm-hmm.
instead of having to think about one algorithm at a time, we essentially have one meta algorithm. All you have to do is write a high-level description and give it to the compiler, and you get an algorithm for your problem.
Yeah.
And that really is an idea that comes from relational database theory, which was the first topic of my research. That my PhD dissertation was about database theory. And only in the last few years, I started to try to socialize the concept of logical algorithmics.
And parameterized algorithms and complexity was already at that time topic too, or that was something that only developed later as well?
It actually independently, it completely independently was developed later in the late 80s. And it took some time before I realized and other people realized that these are both, that all of these are manifestation of multivariate complexity. Okay, it wasn't immediately obvious. The people who discovered parameter complexity did not, even if they knew about my paper, that was not, I'm not saying that was their inspiration. They had a different, I think, independent inspiration for their work. But later you realize, this is all part of a bigger picture of multivariate complexity theory.
What do you think where this will develop further, this multivariate complexity, or what are like questions there that are open today that you think would be very nice to see, PhD thesis on?
So right now, I still have students that are in some sense working on this. One is we are taking this idea, we're taking, instead of looking at database queries, which I have not looked at for a while, we look at essentially concern satisfaction problem, where again, you kind of have the same thing, which is you're writing constraints and you're trying to solve them, and you can think of it as some kind of a query.
Yeah.
You have the domain over which you're you're writing a constraint, you're writing the constraint, so it can be thought of as a query. And a question that have been on my mind now for quite a few years is we have this concept of tree decomposition. And it's a beautiful theory. And the question I've been working on now for about 20 years is, can we use tree decomposition to help us in evaluating queries? Can we find a tree structure there, or almost tree? What are tree decomposition? Tree will tell us how close you are to being a tree.
Yeah.
Can we use this to evaluate queries faster by discovering the inherent treeness of the queries?
Yeah.
And when I first started looking at it, I think it was in maybe 2003. People said, well, tree decomposition is hopeless because the problem itself is intractable. Finding the tree decomposition of a graph is NP hard.
Right, but you have good approximations there.
But by now we have not just approximation, but now you have tools.
Right.
By now you have good tools. It's not enough to have approximation. You need to have good tools. But by now the difference is between now and 20 years ago, and people are building good tools, and there is a competition, and tools are getting better.
Yeah.
So 20 years ago, when we looked at it first, we said, no, hopeless. Let's find another way to attack these queries. But now we can say, okay, let's try to use tree decomposition, and every year the tree decomposers are getting better.
Right.
So this is part of the same revolution that is happening, for example, in such solving, that problems that we thought were intractable are actually quite tractable. In practice, we don't know exactly, we don't fully understand what does it mean to be tractable, okay? So we used to define tractability as well, tractable means polynomial time bound.
Yeah.
And then there are two important, I think, kind of experimental discoveries that put, to me, huge question mark about this, in some sense, one of the most fundamental assumptions in complexity theory. One is that we are able to solve very large SAT instances, okay? We can't say anything about the worst case complexity, but we're able to solve very, very large SAT instances that come from real life in some sense, okay? It's very easy if you go to random benchmarks, few hundred variables, and you get very, very hard problems. But you go to industrial benchmarks, and they're just not that hard for reasons that we don't even fully understand at this point. Okay? So this is one observation, that what we thought is hard is not hard. The other observation is that what we thought was easy is not that easy. So we thought that polynomial time, we said polynomial time is tractable. But the truth is that this will only be true for very low degree polynomial. And typical algorithm people develop often were linear or just n log n or even quadratic, maybe cubic. But then you find algorithms that are n to the 11. And with huge constants. So I had a master student that did his master thesis on computing the permanent.
What's the permanent?
The permanent, you know, when you look at the matrices, when you take the sum, you compute the determinant.
The determinant, yes.
And the determinant has plus minus. The determinant has plus minus. This magical thing, which is depending on the parity there.
Sure.
The permanent, everything, all the coefficients are 1. Okay.
I see. Okay.
Okay. And that was classical result by Valiant that this is sharply hard. So it is hard to compute. Okay. So people work very hard and they show that this problem is in FP-RAS. Okay. But the algorithm has high degree polynomial and huge constants. So the student did some analysis to see, okay, well, asymptotically, this is still better than exponential. But was able to show that if you see when will the exponential become larger, it is for such a large n that it is hopeless. We cannot solve such problem by either exponential or polynomial techniques. And so the conclusion from this that for problem that we can solve, this beautiful polynomial time algorithm, it's an FP-RAS, fully polynomial randomized approximation scheme, is useless. Just use an exponential algorithm and it will perform better than a polynomial time algorithm.
Nice.
And so we made two discoveries. One is that what we thought was hard is not so hard in practice. And also in practice, what we thought was easy is not so easy. And so this completely scrambles how we thought about complexity theory for, by now, you know, 60 years. We started in early 60s. And the whole purpose of complexity theory is to help us understand, I mean, the motivation for that. People start running programs in the 50s. People start building, they have computers, they write all kinds of programs. And they discover that some problems are easy and some problems are hard. Some problems take a lot of time to solve and some problems are easy, okay? And so they try to understand, okay, what can we explain the source of easiness and hardness? And complexity theory is a beautiful theory that offers us an explanation, except that if we want to understand how the complexity of computing in practice, complexity theory actually does not offer as much insight as we thought it does. And to me, this is kind of almost revolutionary. You have one of the most beautiful theories in computer science. You know, this beautiful theory have a beautiful problem, P versus NP, that many people think it's the most outstanding problem in theoretical computer science. And now we discover that this theory offered us very little insight about how algorithm will behave, how the hardness of problems in real life. Of course, if you have an algorithm which is very low degree polynomial with very low constant, it's likely to behave well. But I mean, there is a book that I read about a decade ago in economics, and it's called The Fables of Economics. And it's written by a very distinguished economist, Israeli economist, Ariel Rubinstein. And he basically said, look,
I know him actually.
economists study, yeah, he's done important work in bargaining theory and things like that.
Right.
Okay? He's one of the most distinguished economists in Israel.
He was at
And
Hebrew University, or
he was
where
at Hebrew
was he?
University. And he explained that economists study mathematical models. And the results are typically results about mathematical models. How does that relate to the real world? He said, that's a whole other story. And he said, ultimately, if you need to make economic decision in the real world, you can be informed by mathematical models, but ultimately these are decisions about values, about politics. You know, the idea is that that economic theory will tell us what to do, how to really make make economic decisions in the real world. He call it a fable.
Yeah, okay,
and so
I see.
I think I need to write something that will call, you know, the fables of complexity theory.
Yeah, that sounds nice.
Yeah.
Looking forward to it. Also, regarding going back to the query, like, do you think the languages would also have to be adapted? That, like, you could use more of this, you know, multivariate complexity or three width, or you plan to do this for like existing query languages and query types?
So I had a master student that showed that you can. We couldn't at the time. This was 15 years ago, 20 years ago. We couldn't compute the true widths at the time, but we find a way to approximate it heuristically. So it's not a formal approximation. It's kind of with some heuristic that enable us to compute a tree decomposition.
Yeah.
And we were then able to improve on the performance of performance of queries exponentially. I mean, we had some event in the department, and we had a graduate student put posters. And in addition to putting the posters, everyone got to have to offer a 2-minute elevator pitch.
Yeah.
So people will decide which poster they need to go to.
Yeah.
And his elevator pitch was, here's the, you know, I'm looking at relational queries, and here is how the query is here is how Postgres perform. Postgres is a kind of an open source database, very widely used. And he shows an exponential curve.
Yeah.
And here is how my query optimization perform, and it shows like a straight line, something incredibly better, exponential improvement. He says, and he won the best poster award. And his poster was not that outstanding, except that it shows just everybody liked it to see. You see such a, you know, it's rare that you see such a sharp separation. Here is what a Postgres, almost essentially a widely used database does. Here what the master students can do. And so he won. I remember that people says, wow, it was such a dramatic difference. We had to give you the award. Now, what happened with that paper, we first published a paper in a conference called EDBT, Extending Database Technology, which is
I know it, I think.
somewhat more system/theory. But then he wrote another paper and he wanted to publish it at PODS. And PODS is Principle of Database Systems. And I thought that we are trying to take database theory and reduce it to practice. So this is principles. But the paper was rejected because we didn't have any theorem in the paper.
Yeah.
And I was not happy, not because the paper was rejected. You know, paper get rejected. This is life. We all have to, you know, we are big boys and girls now, and we get our paper rejected. But the reasoning is the paper was rejected because there's no theorems in the paper. That really, I said that this is something wrong with this community if they don't see that reducing theory to practice is a matter of principle.
Right.
So then I kind of, and he was very disappointed. So he left the PhD, and
No.
I never continued that research direction.
Mm-hmm.
But I think it's still there waiting for someone to pick it up, especially
Yeah.
now that we have today. I would have done it, with real 3D composers. Okay, and there are interesting research questioning, which is most optimization, so-called cost-based optimization. Just search for the best plan to do something. So
Mm-hmm.
can we combine structural optimization with cost-based optimization?
Yeah.
So there are interesting questions, but one thing that as one travels along one's career, you realize you have more ideas than you have time to pursue your ideas.
Mm-hmm.
When you have fewer ideas and time, then maybe it's time to retire.
Right.
But as long
Right.
as you have more ideas and time, then it means that. But it's always painful because you see other things to explore, and you just, you don't have the time, you don't have the
Right.
students, you don't have the funding. You can't do it all. So life is a depth first search. This is, if you want, the motto. Life is a depth first search. It's not breadth first search.
So how do you manage your time, or do you have any
I don't.
recommendations for
No.
people how to? This is individual thing, I guess,
I'm
then,
I'm
or
I'm I'm not a very necessarily very good time manager. I scramble all the time. All the time, I say people it's like I'm juggling 7 balls. Any given point, 3 balls are on the floor because I cannot juggle so many balls. And hopefully one of the ball will scream, "Hey, you left me on the floor for too long." And I said, "Oh, I'm so sorry. I'll pick it up and toss it." So I have a hard time just keeping up with email because the volume of email that comes, I can just sit all day and just reply to email. So
no, this I can imagine, of course.
um, I don't have a good system. If somebody has a good system, I'm happy to learn. That you do have to learn and to say no. This morning I
Right.
get a request for someone who met me in a conference. We have a nice discussion, and he asked me if I would write a letter of reference for him. And I love to help, but the answer is I can spend all my time just writing reference letters, and I probably write at least 1 letter per week.
Yeah. Yeah.
So at some point, I just realized this can become a full-time job, and I made a decision that I only write letters for students and collaborators.
Yeah.
And and there are people who think that, who knows, a letter for me might open some door for them. And I have to say, maybe, but I just,
It's just not
life is
possible.
finite, time is finite. So it's a painful decision that you have to accept at some point.
No, of course. I have a colleague, when he come back from holiday, he deletes all his emails just to start from scratch, and he says the most important anyway will come back.
So
But
I do it at the end of the year. I take my whole email file and I archive it. I don't delete it.
nice.
That would be
Okay.
too
Nice.
irresponsible
Yeah.
for me. I
Yeah.
archive it, and then I start the year with an empty inbox.
Nice. Oh,
And
that's
every year, I
nice.
think maybe this year there is a people who practice what they so-called zero inbox policy.
Yeah.
You need to finish every day with an empty inbox, and
Yeah.
I've never
Yeah.
been
Yeah.
able to do it.
Yes.
But
No, that
every
can
year, I
imagine.
hope maybe this year I'll be successful. So far, I have always failed to do it. So I have a
Yeah.
whole, gigabytes and gigabytes of email that I have not been able to respond
Yeah.
to. And again, part of the issue is you assume if something is really important, somebody will come back to you and with a more urgent headline, subject line. So I don't have a good solution to
that. When and where is your most productive working time or place?
I'm not a night owl, and I'm not, I have normal working hours. So I get up every day at 6:30, but there are some people who wake up at 4 o'clock because they like the quiet hours of the day before everything. I don't like to get up too early. 6:30 is a nice kind of compromise for me. And I think sleep is very, very important. So I try to be in bed by 11 o'clock. So just be disciplined. It's very easy. There's always, remember, the inbox is always there saying, read me, read me, read me. So I could always tell later and later, just replying to email. So you just have to have, one of the things when you have a longer career is to realize it's a marathon, not a sprint.
Yeah.
And that means that you have to pace yourself. There is a beautiful story about the London Olympics, one of the first Olympic Games in London, early 20th century. There was an Italian marathon runner who ran very fast. and he was way ahead of everybody else, but he ran too fast. And about 50 meters before the finish line, he collapsed.
Oh,
But
yeah.
he was so far ahead of everyone else. Everybody was yelling at him, "Get up and walk. If you just walk, you'll win. You'll get the medal." But he was too exhausted to get up and walk. So finally, the referees couldn't help themselves, and they ran to him and helped him to stand up
Oh, really?
and walk.
No.
But
Wow.
then he was disqualified, of
No.
course. Yeah. So I remember that
Yeah.
story, and I just, you have to
Oh, that
pace
makes
yourself.
sense. I agree.
You have to
And in
pace yourself.
terms of place,
There was
do you have
one
any?
time, maybe in the early 90s, like almost 30 years ago, that I tried to spend an all-nighter to finish a paper for like, when the deadline is like, midnight anywhere on earth, which is like 6
Yeah, yeah.
o'clock here.
Hmm.
And at about 2 o'clock in the morning, I realized that my writing is becoming crappy because I was very tired. And I decided, you know what? This paper will not be written, will not be submitted to this conference. And that was the last time I tried to pull an all-nighter.
Yeah, it was not worth it.
I decided after that again, it's okay, you're a PhD student, you do these things, but
Yeah.
you have to start thinking about the long term.
All right.
I've never tried to do an all-nighter after that.
Yeah. That's nice. Actually, I was about to ask you for a nice anecdote from your career that you'd like to share with the readers, but I guess we already have some. But if something
This
comes to
is
your
one.
mind, tell.
Here's the more dramatic anecdote. So this is one of my, again, I'm still a postdoc. I had a paper in, I think it was Fox, maybe 85. And I was the sole author. And my paper was on the first day of the conference. And in the reception, a colleague of mine, collaborator, Pierre Wolper, comes to me and says, "I saw the paper in the proceedings. I start reading it. It's a lovely paper. I just got stuck on this proof." I said, "Okay, I'll go and double check it." So I go to my room and I spend all night trying to fix the proof. There was a bug in the proof, and I spent all night trying to fix the bug, and I couldn't do it.
Wow.
My talk was in the morning session.
Yeah.
So I'm a young postdoc. I have to go to the talk, and I have to say, this is it. Here in this proof, there is an error. I have not been able to fix this error. A few years later, it turned out that the theorem was correct. The proof was incorrect, but the theorem fortunately was correct, and other people proved the theorem. So I didn't publish a wrong theorem, but the proof was incorrect. But it's not a fun moment for a postdoc to come to a major conference and give a talk and have to stand and say, "I made an error." Turn out the paper was still, this is the first paper that tried to do probabilistic model checking.
Yeah.
But the paper was actually quite influential.
Yeah.
But at the time, it was very, very challenging to stand up there and to say,
That's
"I have a bug in the proof. I've not been able to fix it."
Yeah. Brave that you still did that. So
Yeah.
it's unusual that the evening before the presentation you get a comment like this, right? So during the presentation, but that's of course stressful, I guess.
Yeah. No, this was an all-nighter. I pulled all night. I tried all night to fix it, and I couldn't fix it. No, the proof was fundamentally buggy. A new idea was needed, and other people found it later. But I was not able to find it during that long night.
Do you have any advice for young researchers, in what to invest time or what should they avoid or
So I think, there are I'm not in the advice offering business, because I think that everybody has, there is a phrase I've heard from a colleague of mine. We said, people are like trees. You have to grow where you are planted. Everybody is a unique package of strengths and weaknesses. So everybody has to figure out what works for them, what makes them successful. What works for me may not work for other people.
That's right.
So I mean, this assumption that somehow people 7 rules for successful career or things like that.
That's right.
I've never find that something I read, "Oh wow, this is really inspiring." It just always feels that you should do what works best for you.
Right. And among your students, do you see some pattern or something that you think in general maybe could be avoided?
My students are very different. So in fact, I discovered that I'm not always a very good predictor for my student success. And the reason is because I tend to judge them on their technical capabilities.
Mm-hmm.
And because that's what they do. PhD, you do technical work, and I tend to
Right.
judge them on these technical capabilities. But it turns out the technical capabilities is not necessary nor sufficient for a successful career.
Yeah, yeah.
So there are people, and I've seen people who are very, very smart, but not very wise. And one of the things that you in life, you're not a theorem making machine or paper writing machines, okay? You are always working within a social context. You know, you're working in a department, you have colleagues, you're working within a scientific community. It has its own norms. And so there are people who knows how to manage their career. And such people very often, they may not be strong technically, but they may end up having more successful careers than people who are very technically very strong, but are somehow tend to be somewhat clueless about how to manage their career. I don't know if you ever watch. Did you get in Europe Big Bang Theory?
Yes, of course.
And so think of like Sheldon Cooper is a kind of example, right? Incredibly brilliant, but not always, you know, his understanding of how the world works is very, very imperfect at times, right? So, and you see around you, I've seen such people. I've seen people who are very smart and they crash and burn. And I've seen more than once people who are so strong that they get over ambitious. And what I mean by that, they think, okay, I will make my name by solving a very hard open problem. That's how they want to make their mark. And of course, if you succeed, yes, that's going to be, you know, you solve one problem and you're going to make your mark. But the open hard problems are open because they are very hard. If they were not very hard, somebody would solve them by now. So it's a dangerous strategy to focus on just I'm going to focus on a very hard problem and I'll do my hardest, my darnest to solve it. Okay, if you succeed, good. But what if you don't succeed? So I always advise people to diversify the research portfolio. Don't work only on one problem. You never know when you start working on something how hard it's going to be. And the other thing is, you know, I had a postdoc. He came and tried to interest in some problem. And I said, no, I'm not going to get involved in this one. And he said, why not? He said, it's technically interesting, but I'm not sure it is interesting in a bigger scheme of things, okay? Just because it's a technically interesting problem doesn't necessarily make an interesting problem. It's very easy to define mathematical problem. And I've learned this from, actually, I was still really a young postdoc and I worked with a more senior colleague and we going after someone and it was hard and we were making more an offer. And finally he said, is it worth putting all of our time into this problem? Suppose we succeed, what will be the big result here? And I said, truth of the matter is, I don't know, I don't see either. So we just decided to abandon the problem. I don't remember what the problem was. We just decided it was not worthy much of more of our time. And this is a decision you have to make sometime. You start thinking about something and then you have to think, okay, how much time should I invest in that problem? And that means you have to be, again, somewhat strategic about what should I work on? You know, what will be the impact if I get a result? What will be the impact? Who will care? So it's not just enough to be technically interesting. It has to be, you should ask, will people care? Will anybody pay attention if I solve this problem? So the bigger picture, which is how to manage one's career, is as important, if not more important, than just being able to solve problems. I've seen people who are very good at having a vision and writing good proposals and getting funding and using the funding to bring good students. And they are not necessarily very strong technically themselves, but they can create an environment. They create a strong research group by having the vision.
So it's also a talent or something that can be learned.
So when in my group, everybody has to give a talk, has to do a dry run. And I always tell them that a talk and a paper will end up stand or fall on the story. So you have to tell a story. It's not just I have a theorem.
Right.
It has to be a story. Human beings are
Right.
sucker for stories,
Mm-hmm.
okay?
Mm-hmm. Mm-hmm.
We read novels. And
Yeah.
you ask, why are we reading novels?
Yeah.
A novel, a fiction, when you read fiction, you're reading a story that never happens. It's a fiction, right?
Right.
Why would you care about characters that you know do not exist? Why would you care
Yeah.
about their troubles? So it's an interesting question psychologically. Why do we care about
Mm-hmm.
things that we know never happened?
Mm-hmm.
And apparently the best people have the answer is that it's a way for us to simulate the world. It's a safe way to create simulation, to see what happened in, to experience different scenarios of the world without having to take any risk ourselves.
Yeah.
But because of that, we are sucker for stories. You go to even on kind of culture, you find all culture has the concept, you look at some of our early literature, the story of Gilgamesh,
Mm-hmm.
about what is it now? Probably about 4,000 years old, if not more. People love stories.
Right.
It is part of human nature. We love stories. So a paper has to have a story.
Right.
Okay.
Which
If you
also forces you to think about the vision for it or putting it a bit into a context or
into
so. Right.
context. So in fact, there
Right.
is a way, there is a universal structure. I learned it from somebody told me, oh, take a look at what's called the three acts. I talked to someone about the story, and he said, oh, you should take a look at the three act structure. So what is it? It's a literary term. Go look for it. So I go read it. And he
Okay.
said, all stories have a universal structure.
Yeah.
Introduce the characters,
Yes. Okay.
create a
Yeah. Yeah.
crisis for the characters,
Yeah.
resolve the crisis.
Yeah.
And so this is
Right.
how you tell a scientific story. You
Yeah.
give
Yeah. Yeah.
background and motivation.
Right.
Then there must be something we don't know how to do. There must be a
Yeah.
crisis, right? An open
Yeah.
problem.
Yeah. Yeah. Yeah.
Otherwise, there's nothing to do. If everything has been
Yeah.
solved, there's nothing to do. There has to be a
Right.
problem, and then you come as a knight on a
Yeah.
white horse, and you save the world.
Right.
Okay, this is a very very simple structure, but
Yeah.
if you
Yeah.
tell that structure, then you have a story.
Very nice. What kind of features do you look for when searching for graduate students?
I don't search for graduate students, so
Right.
they
So let's say they come for you and you
they
have to
usually
select
come
them.
for me, and they usually have taken my class, and then they come and say, I'd like to work with you.
Right.
And I usually say yes to everyone.
Ah, really?
And yeah, I don't know that I ever, it's different. People, I get email every day. I get an email from someone. Can I be your student? I mean, really, every day. And I always tell them, you should apply not to me, because there is a difference between the way we do graduate admission in Europe and in the United States. In Europe, very often the professor accepts a student.
Yeah.
In the United States, we view it as a departmental program. So students apply to
Yeah.
department, and the
Yeah.
departments admit the students.
Yeah.
And this means the department takes a responsibility for the students.
Yeah.
So if the students maybe did not get along, maybe the initial advising relationship did not work out, the
Yeah.
department will make an effort to find another advisor. Okay. To say, okay, maybe it's just a matter of relationship. If
Yeah.
the student didn't work at all, something, but in many cases we say, okay, we'll try another advisor.
Mm-hmm.
And I had some students that I took from another advisor because the first relationship did not work out, and I've taken on such students. And so I always tell students that are interested, I said, apply to RISE. That means if you come to RISE, you'll be able to then choose an advisor.
Mm-hmm.
And I don't think I ever declined a student. And every student that I take, we get students here again. The difference is that we don't have, like in Germany, you have the diploma after the bachelor.
Mm-hmm.
Here we get students with a bachelor degree.
Right.
And my commitment is, every students that come to me, I will at least get them to the master's degree.
Yeah.
And I have lost 2 students because they have their own issues.
Yeah.
I try to stick with the students as long as possible. Okay. They're willing to do some work, I'll get them to a master. Mm-hmm. What happened is, some students, after getting the master, I tell them, look, I don't think a PhD is the right track for you, at least not with me.
Yeah.
But every student that I've taken, I said, I've lost 2. that I've lost a few. I've lost two that left before finishing a master's degree because they have their own issues.
Yeah.
But every other student that started working with me at least got a master's degree. And then I tell some of them, okay, I don't know that I'm a good advisor for you. You should consider finding another advisor, in which case very often they decide, okay, I'll drop out of the program.
Yeah.
But at least they have a master's degree.
Right. Okay, nice.
Yeah.
What do you see challenges and opportunities for theoretical computer scientists in the near future?
So I think the computer science field keeps changing, and that means there are always new questions. For example, to me, there is a huge questions now, really a call to redo complexity theory. Okay, I mean, complex theory explains less and less well the world. Okay, so we had a theory that was supposed to give us the explanation for what is it, what is hard, and it doesn't. And I don't think the conclusion is the theory is no good. I think the answer is just like in any other, if you look at physics, when there's discrepancy between the theory and the world, we have to come up with better theories.
Right.
I remember talking to a physicist some years ago about all kind of experimental, in cosmology, I mean, all kind of problems. And I said, well, it looks to me like physics is in crisis. He said, to the contrary, this is a moment of opportunity for physics. This is the time to make new discoveries, to come up with new theories. So the fact that the current theory does not explain the world very well, physics, we are saying, oh my goodness, what happened? Physics will say, fantastic, now we can become inventive again, okay? Now we can innovate and come up with new theories. And in particular, we have this amazing success of machine learning, of deep learning, of generative AI. We don't fully understand what's going on there. And can theory shed some light on it? Okay. I mean, so the experimentalists don't care. Okay. But one of the success story of theory is that good theory end up being also useful theory. Okay, so I look at the case, my probably biggest success is in automata theoretic model checking. And there, all the theory was there kind of before me, the connection between logic and automata was laid out before me. And it was done by, again, people who are not thinking at all about practical things. They just want to understand, how do we decision procedure for monadic theories. And everything they did was non-elementary, but it was there. And Tarski did fixed points, the theory of fixed point. And again, it was all very theoretical. And then we're actually all of this gave us gave rise to industrial tools. So this is amazing success of theory. That elegant theory end up being actually very useful. Now, there is this debate about beauty. What does beauty mean? So some people, there is this belief, something so beautiful, it must be true. But this is debatable. Complex theory is very beautiful. And as we say, it's not a good description of the world. In physics, there is string theory. And many people, physicists, say string theory is very beautiful, but it led us astray. It does not take physics in a constructive direction. I mean, I know it's a matter of debate. I'm just saying there are people who argue that. So beauty does not always necessarily lead to usefulness. But in the case, for example, of automata theoretic model checking, the simplicity of the algorithm, and the story what the paper was at first rejected, the paper by the Vardi Wolper paper was first rejected because the reviewer said it's too simple. So Per and I added another section on probabilistic model checking, which was very complicated. And so the paper was accepted. Nobody ever read the complicated section. The whole beauty of the paper is to show this is actually very simple. The construction can be modularized, go from LTL to automata. If you go later, we find in another way, go to alternating automata first and then to automata, and then you do the whole thing. And the simplicity meant that it was actually easy to implement it. And I was a theoretician, but I give credit to Doron Peled, who came to me and said, this sounds pretty simple. I think I can implement it easily. And so the simplicity turned out to be not so much a matter of beauty, but as a matter of it's easy to implement because it is simple. And so in this case, simplicity led to implementation. So I think good theory has huge potential, all the way to one of the, I think, huge success story in computer science, relational databases, where Ted Code said, let's use first order logic as a query language. And the system, people say, out of your mind, will never perform well. And now, you know, relational databases are the foundation of Western civilization, so to speak. So good theory has tremendous potential, and there are always new applications, new ways to look at the world.
Oh, nice. I did not know this, actually. People were at that time having very big concerns about first order logic for databases.
Yeah. In the mid-70s, there was a period called the relational wars.
Okay.
Because Code came up with something very radical, which is a declarative approach to the whole problem. And all the query languages until then were imperative query language. Go to this record, test a pointer, find a connection. How do you do a join? Find a tuple, find a value, go to the index, look at the pointer, go to the other one. It was all very imperative. And Code says, this is a mess, let's do it declaratively. And people said, a theoretical idea. It will never work in practice. And there were already industrial software that doing it, so the people had a vested interest in. You basically told them your software is it's a bad idea. You should do it differently. So there was a huge fight inside IBM. If you Google the relational wars, huge fight in around mid-70s over this idea. And ultimately, by 81, I mean, this was a very fast Turing Award. He wrote the paper in 1970. 11 years later, he gets a Turing Award. But in between, there was a huge fight over this.
But at that time, it was clear to everyone that this was like the right approach. Then 11 years
It was
later,
a big fight. I mean, what happened, there were two projects that people had to show that it's going to work. And there was System R at IBM Research and Ingress at Berkeley. And both of these projects shows it works. And as they said, the rest is history. But people have to implement it and to show that they can make it work. Non-trivial. It was non-trivial effort to do all the query optimization to show that you can make it work. And it worked, and it changed the world.
Can you recommend some source of information that you're using, like or enjoy, like a blog post or a YouTube channel or a book or something that you recommend to the community to have a look there?
There is a book now. That one of my books that I like very much is by Martin Davis. Let me see if I can quickly find it. Martin Davis passed away a few months ago. He was in his mid-90s, but he wrote what is it called? Okay, Martin books. Let me go there. I forgot the name of the book. Engines somethings. Let me see. Books. The Universal Computer. From Leibniz to Turing. You kind of tell the story of how computing arose, but kind of going back all the way to Leibniz. I'll put it on the chat. And one of the things that we don't do in science and engineering in academia, at least in the United States, we teach students the facts. This is what you need to know. Here are the algorithms. And we teach them very little about the history of how the things happened. So students end up, they may know a lot, but they completely lack a sense of the historical dimension. That these are all, this idea were developed. And I think it's a mistake to do it this way, because what happened is that that all these great ideas were created by human beings, flesh and blood, imperfect human being. They're all kind of stories. Some of them lived happy life. Many of them lived very unhappy lives. And I think it's a mistake for the students not to get part of this dimension about the fact that this was done by, and get some sense of how discovery come about. So I think at least this is a very nice story of computer science, all the way from Leibniz, who first conceived of the idea of mechanical computers, we call it calculus ratiocinator, all the way to Turing. And I'll put another thing on the chat, which is the talk. I try to do it in 1 hour to give a talk. I call it From Aristotle to the iPhone.
Okay.
In which I try to take that story and tell it in 1 hour, which is, of course, as you know, whenever you try to do it, many, as I say, many pieces are left on the editing floor. You can tell, you cannot, Aristotle to the iPhone. You can't, in 1 hour, squeeze the whole story. Okay, where is that thing? Okay, here it is. So once everything's, oops, sorry. So you can include the link.
That will be nice. We can actually put it into the article, the
here
reference
it's
there.
in the link. So this is a popular, this is very popular version. It goes to for a broad audience. Let me see how many people have watched it by now. 8,000 people watch it so far, so it's not bad. So it's kind of a very nice. I try to make it. Remember, I like stories. I try to make it a story. Okay, and in fact, I got the insight for this. I gave this talk. I don't remember. I've given this talk in different versions over the years, but once I was supposed to give it in UCLA for an event that was meant to attract all kind of alums, alumni.
Right,
I sent them the abstract, and the organizer came back to me and said, "Yeah, the abstract is good, but it's a little bit dry. Can you make it a bit more lively?" So I added one sentence. to the abstract. I wrote, "This is a story where the protagonists usually die young, early, die young, miserable, or both." And I added this abstract. And now it attracted many people. and it suddenly I got the insight, people want to see the human dimension. This one sentence, suddenly people say, oh, this is a good story. This is not just about alpha, beta, gamma, delta. This is a story about people. Okay, now we want to hear it. And then I started in 2021. People came up with there is a new thing called World Logic Day. So January 14th is the same date that Gödel died and Tarski was born, or the other way around. I forgot which one. So UNESCO has declared it as a World Logic Day, and people are trying to say every year event should happen around it. So in 2021, and also we are still in the middle of COVID, I decided, okay, I will give a Zoom talk about this. And I contacted the PR person in the department, and I said, could you help me in publicizing this event? And I included a sentence where all the protagonists die young, miserable, or both. And she read the sentence. She says, "Is this for broad audience?" I say, "Yeah, this is going to be non-technical talk." She says, "Oh, so I'm going to do broad publicity for this." Like she sent it to all of our alums and all of RISE, okay, because it's a non-technical talk. And we start. She said, "How many people do you expect?" I said, "I have no idea." So we started publicity, and the department has a Zoom license for up to 300 people. And we use, people had to register for this. So we passed 300. So we went to a license for 500 people. And then we passed that. So we went to a license with 1,000 people. And then we passed that. So we went to a license with up to 3,000 people. And 1,700 people registered.
Wow.
And about 1,000 people showed up for the talk. And I believe that this was the largest audience in the history of the cosmos for logic talk. I don't think there was any logic talk until now. They had 1,000 people. I was blown away by this. Is amazing that because it was people, if I gave a talk, like I think it was a noon talk or something like that. And it means people on the West Coast can attend
as well, right?
And it's and all the way to people in Europe. Okay, it's noon, it's 7 o'clock in the evening. You know, China and Singapore and Australia, that might be a bit too late for them. Okay, but you can cover a huge part of the world,
right?
And 1,000 people showed up. It was just amazing.
Yeah, very nice.
Yeah,
very nice. And this was the one is on YouTube also, right? So that's kind of the same talk there.
This is the one. This is the talk. This is exactly the talk that I just gave you. This is the talk that attracted about 1,000 people. I said, I've been to, for example, the only other big events of logic. There's something called International Congress on Logic, Philosophy, and Methodology of Science, or Logic, Philosophy, Methodology of Science. Okay, big logic congress. Okay, and I've been there, and there you have when you have like a keynote, I would say you have maybe a few hundred people in the audience, but not 1,000, less than 500. I mean, remember, I was there once. It was big, but not less than 500 people. So 1,000, I think. I mean, anybody who thinks they can think of a logic talk with a bigger audience, I'd love to know about it.
So we have a couple of sentences. We would like to ask you to complete them. One is okay. Being a researcher. ...
I do formal languages, so I can complete any sentence by writing star dot star.
Okay, good.
Being a researcher. So I'll tell you a story.
Okay, that sounds good.
So when I was in the IDF, in my training, I had to go to parachuting school. And
wow.
In that school, we had to make 5 jumps.
Even for artillery people. So,
yeah, because sometimes you have to go on a plane, so we have to take a parachuting school. And so I go there, and we have to do 5 jumps. And the way it goes, the plane fly to the dropping zone, and then when it approaches the dropping zone, the red light comes up. Then everybody stands up and the door opens, and people line up from the door. And then about a minute later, you reach the dropping zone, and then the red light changes to green light, and then people start jumping. And the jumping has to happen fairly fast because you want to minimize unit dispersal. You want people to be as close to each other when they come down. And on the 3rd jump, I was somehow delayed, so I ended up being last in line to get on the plane. And then I discovered that the person who is last to get on the plane is sitting nearest to the door. And that means when they open the door, I have to go to the door of an airplane. The airplane is going, about, who knows, about maybe 400 miles per hour, about 600 kilometers per hour. And you open the door and you go to the door. It's like you're holding the door and you're kind of standing there ready to jump. So now you have to imagine yourself. It's plane, the engines are roaring. You are kind of almost almost ready to jump off the plane for about 1 minute. And this feeling of being between the plane and nothingness, between space out there for 1 minute, it's the most alive that one can ever, that I've ever been. Okay. And it was such an exciting, such a rush that I managed to we jumped 5 jumps, and I managed for the 5th jump to do the same thing, to be the last. So I was standing just to stand on the door for 1 hour. And I tell that story to my graduate student, to my PhD student. I said, this is a beautiful metaphor for research. You're standing at the edge of the unknown. Okay? And all you have to do, solve the problem and jump into the unknown. Okay? You're standing at the edge of the unknown. I said, Richard, it's so exciting. Because you are at the edge of the unknown. I tell them, imagine, no one knows the thing that you are trying to solve now. No one knows the answer to that. Humanity does not have the answer to that. You are trying to find the answer. And I use this story as a metaphor for standing at the edge of the unknown. I want them all to be as excited as I was when I was standing there holding the doors of the plane.
Very nice. My first research discovery, dot star.
So my first research discovery, I mean, I started doing research in a almost accidental way. I was a master's student. I had no idea what my research topic would be, but there was a seminar. It was about something called database dependencies. The seminar was about databases, and the instructor, professor, just gave us papers to read, and we should give a talk on the paper. So I got a paper to read, and I end up giving a talk on the paper, just covering the content of the paper, describing the content of the paper. But the paper ended with an open question, and that open question intrigued me, and I started thinking about it. And then I went to the professor and says, I have some ideas about this question. And he said, oh, I'd love to hear about them. And that became a master thesis. And that grew up into my PhD thesis. Nice. And it all started, I mean, there was no intention. When we gave the paper, it was not, this is what, and then before that, he was not even my advisor. He was just the seminar organizer. Okay.
Yeah.
But I read the questions and I was intrigued by the question.
Nice.
And that's how my research career was launched, by just saying, oh, what an interesting question. Let me think about it. Okay.
So that was opportunity based.
So all the students read paper, they always should go to the end of the paper and they see other interesting research questions that they can think about.
Did you stay in touch with the teacher of the seminar there?
Yeah, he became a master's advisor.
Ah, yes, okay.
Ultimately, he became my PhD advisor, and we became kind of lifelong friends. He's in Israel. I mean, I was in Israel. In Israel in the summer. He's quite senior now. He's retired, but I was in Israel in the summer. I went to visit him. You know,
very nice.
Your PhD advisor is you know, a relationship forever, right?
Yeah, right.
Yeah.
Very
and
nice.
All started. Here's a paper. Read the paper and give a talk on it. Yeah, that's how it started.
Now the dot star is at the beginning. Is key to be a happy epidemic, happy academic.
To be a happy academic, you must be very resilient, because being academic, you know, some people have this view, maybe for some movies, that it's a kind of an easy job.
Right.
But being a professor in research university is a very intense job. Okay. And in fact, today, when you look at you know, people get their PhDs, they're usually in their late 20s, you know, 27, 28, maybe 29, maybe something like this, sometime a bit younger, but something like this. I was 27 when I finished my PhD. And, you know, retirement is about 40 years away. Again, it varies. In the United States, we don't have any mandatory retirement, but let's say you have ahead of you at least 40 years. That's a very, very, very long time. Think about it. Okay, go back and 40 years ago and take a look at the papers. And it turns out that having a 40-year-long productive research career is actually very, very difficult. One, it's always competitive. It is not now that now I'm fairly well known, but it's not now that I submit a paper and say, oh, Vardi wrote a paper, so we must accept it. No, I still go, it gets reviewed, and people still reject it. You know, people think that people would somehow show me some deference. It's actually the contrary. People write reviews. I have higher expectations from Vardi. You know, I mean, so I write research proposal, and they sometimes they don't always get funded. Okay, so it is always competitive, and you have to accept that you are human and you're going to win some and lose some, and celebrate the victories. And whenever have defense mechanism, whenever the paper is rejected or the reviewers are stupid, you know, you have to have some defense mechanism to deal with it. It is competitive, and it's always competitive. So people they have a hard time with it. They will not be happy in a research career. And it's, you know, I had relatives that a young woman and she met her husband in a undergraduate school. And when they finished, they got married just when they finished the bachelor degree.
Mm-hmm.
And he said, okay, let's go look for a job. But she grew up next to the Weizmann Institute. So it was her life dream to go there. She said, let's go do a master, let's go do a master's degree.
Mm-hmm.
And this was her life dream, was to be a student at the Weizmann Institute. When they got there, she discovered that she didn't like the unstructuredness of being graduate students. What should I work on today? She went to her advisor. What should I work on today? He said, I'm not going to tell you. You have to figure out for yourself what to work on today.
Mm-hmm.
And she didn't like it. She said, I want to come in the morning, know exactly what I'm supposed to do, finish the day, know exactly whether I did well or not. And the free-formness of graduate studies were not good for her. So she finished her master's, went to find a good job, and she has had a good career. Her husband, who only went to do the graduate school because his wife said, let's go to graduate school. He loved it. He flourished there and he became an academic.
Nice.
Okay? So, you know, a risk career is not right or wrong. It's good for some people enjoy it, and some people discover they don't enjoy it. And everybody has to decide what makes sense for them.
No, very nice.
But it is competitive, and it's a marathon and not a sprint.
Okay, last question from this list. Theoretical computer science in 100 years from now.
Ooh, boy, that's a tall order. So I think, I'm hoping that that theoretical computer science I still think it's, in some sense, it is still young. You know, it's hard for us to see it because we say, you know, I mean, we look at some of the people who started and they look old to us, right? You look at the people who started computer science, you know, in the theory, theoretical computer science started really in the 50s and 60s, and it seems like a long time ago. But as a discipline, it's still a very young discipline compared to other disciplines. And as I said, for example, we had the beautiful theory, complexity theory. Now we're realizing it's actually immature. It does not offer us a good explanation of the world, of the practical world. So I think the theories will mature. I would love to come back in 100 years and to see what does computer science, how this dilemma of complexity theory versus the world, how was it resolved? Did people just decide to ignore the theory? Or my hope is that there will be a much better theory that, you know, will not replace the theory of today. It will refine it. It will bring more nuance to this. It will say, okay, it's NP hard. Okay, what now? And even the thing that we have not now, okay, we say, okay, is it approximable? But even that doesn't tell us how will it behave in practice, how will it behave on realistic, on real life problems. So my hope is that we'll have a theory that will give us better answers. Okay. So this is my hope. The theory will mature. The same way, if you look at other theories, we started with theories, and we discover, you know, we have classical physics, which was beautiful theory. So much so that I think it was Lord Kelvin who pretty much said around the turn of the century, pretty much we've solved all the problems, except for a few, you know, black box radiation or things like that, few problems. It was a beautiful, you know, if you study, when I was a physics major, and you study in year one, you study classical mechanics and electromagnetism and optics. It's a beautiful theory. It just doesn't explain the world good enough, well enough. So let's give the whole rise to even more beautiful theories to come. I think we are at that stage. We are only finish year one in some sense, and the best is yet to come.